In this chapter, what we were doing was we were talking about temperature and heat. Okay. Now, and we saw, we started off by seeing this little app. What this is a gas, and this gas is at 300 degree Kelvin, which is the room temperature, which is the temperature in this room. Okay. And what temperature measures is, it measures how hot an object is. But what it tells you is what is the average kinetic energy per molecule. That's what the temperature says. So when you heat up the gas, what you're doing is you're increasing the kinetic energy of each molecule. Now, you see that not every molecule is traveling at the same speed. Okay? So there's a distribution of speed, and so roughly this tells you the distribution of speed is like this. So here is the speed. By the way, the average speed of the gas molecules in this room is about 0.5 kilometer a second. Okay, so the gas molecule will go across this campus in 1 second. Okay. So if you plot the number of molecules with this speed, you would get a graph something like this, okay, at a given temperature. Now, answer this very carefully. What will happen if I heat the gas? What will happen to that graph? I'm sorry? The molecules will move faster. So what would happen to this graph? Okay, so you will have more molecules going faster. Okay, you're not changing the number of molecules, so the graph will shift to the right. Did you guys understand that? Right, so that's what will happen. Okay, anyway, what we want to remember is temperature is a measure of the average kinetic energy per molecule. Okay, so that's what we learned that last time. All right, so temperature measures the average kinetic energy per molecule. So for instance, this is a solid. This could be your the table in front of you. And if this end of the table is hotter than this end of the table, unlike in a gas, in a solid, the molecules do not leave their average position. So when this end is hotter, these guys are vibrating with a greater amplitude. They have a greater kinetic energy. This end of the table is colder, so they don't vibrate as much. Okay. Okay. So that's what temperature tells you. Okay. Two objects are in thermal contact if they can exchange heat with each other. Okay. You are in thermal equilibrium when you have the same temperature, and there is no net exchange of heat. Okay. Okay. So we saw a very interesting phenomenon last time, and let me remind you again, you guys go ahead and grab the metal on your chair. And then touch the table. Those two things are at the exact same temperature, but the metal felt colder. Why is that? There's a, yep. So what concerns us, it's not temperature, you're losing energy faster, heat faster, okay? What concerns us more is not the temperature, at what rate you're losing heat or gaining heat. Okay, that concerns us faster. Okay, so that felt colder because the metal felt colder because you were losing heat faster. Just like that, it's not how hot an object is. If you touch a hot object, what concerns you is how much heat is flowing into you. Okay, the more heat flows into you, the more damage it does. Okay, so anyway, that's what we're saying here. Okay, there are three commonly used temperature scales: the Celsius scale, Fahrenheit, and Kelvin scale. Okay, to make any temperature scale, you need two physical phenomena. Okay, so here's the freezing point of water, and here's the boiling point of water. Okay, this scale calls that 0 degrees Celsius. 100 degrees Celsius. This scale calls the same temperature 32 degree Fahrenheit, 202 degree Fahrenheit, and so on. Okay. These formulas let you convert from the Celsius scale to the Fahrenheit scale. This formula lets you convert the temperature from the Celsius scale to the Kelvin scale. Okay. To go from Celsius to Kelvin, all you need to do is add 273 degrees. Okay. You guys remember the absolute zero concept? What is the absolute zero?
The lowest temperature.
Yeah, that's the lowest temperature possible. Okay, good. Right, so you saw that temperature was a measure of the kinetic energy of these particles. And you know what is the best you can do? You can stop all the molecules. And you can't cool anything colder than that. Okay? And when you stop all the molecules, you've reached the lowest possible temperature. Okay? And that's absolute zero. So we saw all of that. Here are some of the temperatures that are measured. Okay? And so I'll show you one more important simulation. Okay, this is called a black body spectrum. Okay, what this is the intensity of radiation coming from an object, and this is the wavelength. The wavelength relates to the color as well. Okay, so if you heat any black body to this temperature, for instance, so that's the surface temperature of the sun, 5,800 degree Kelvin. What it'll do is, for this color, it'll emit that intensity. For this color, it'll emit that intensity. For this color, it'll emit that intensity. Okay, at this given temperature, that's a fixed curve. Okay, so for instance, if you heat this table in front of you to that temperature, that will emit these radiation. This color, it'll emit that intensity. This color, it'll emit that intensity. Okay, if you heat the table to this temperature, okay, it'll emit this color at that intensity, this color at that intensity, that precise intensity. Okay, so to measure the temperature of the table, you don't have to touch it. All you have to do is measure intensity of 4 or 5 different colors, and then you can get the temperature of that object. Okay, and that's how those no-touch thermometers work. Okay? So this is the black body spectrum, okay? And that's how you measure the temperature of any object that's remotely. Okay? So we saw that, and that's very important. All right, so when you heat a solid, it expands, and it expands because the solid is modeled by these atoms with the forces between the atoms modeled by springs. And the spring will stretch when you heat an object, potential energy increases, each atom moves further apart, and so they stretch. The solid length, the solid's length increases. And so you have to account for that in structures like this. Okay? So this bridge in Michigan sees a 100-degree rise in temperature between the dead of winter and dead of summer and the peak of summer. And that's what, so all the bridge spans will expand, and that's the expansion gap. So this is the gap between the spans in the winter, and the gaps have closed in the summer. Okay? So you got to make sure that you leave enough of a gap, because if there's not enough of a gap and if the spans push against each other, something like this would happen. Okay? All right. So here's a model of a solid again. In a solid, atoms are in a fixed location, okay? And at any given temperature, they're vibrating about their equilibrium position. And also there's potential energy between them. When you add heat to them, their kinetic energy increases and their potential energy increases also, because the springs stretch. Okay? So if you have a solid at a higher temperature in contact with the solid at a lower temperature, what happens is some of the kinetic energy and the potential energy goes there. okay? And heat flows from here to there. So heat is a combination of the kinetic energy and potential energy of all these atoms, okay? So that's the random internal kinetic and potential energy, which is what flows over there. All right, so we saw all of that. Um, so here are some units of heat energy. Calorie is a unit of heat energy that was used in the past. Now, in SI units, joule is the unit of is the unit of energy. Okay, so we try and use the joule for everything, but the calorie is still used quite a bit. And a calorie is the amount of 1 calorie is the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. And you guys all know 1 gram of water is about a little cap full of water. Okay. C is the specific heat. Okay, so when you heat a substance, the amount of heat that when you heat a liquid or a solid, the amount of heat you've added is the amount of the mass of the solid or liquid times the specific heat times the rise in temperature. Okay? So if you have 1 kg of solid and you raise the temperature by 1 degree Celsius, that's how much heat you would need. Okay? So that's what that formula tells you. All right, let's see if you guys remember the story from last time. Okay. So the density of a material is how much mass there is per unit volume. Okay. When you raise the temperature of most objects, the volume increases, the material expands. If this increases, the mass is not changing when you're heating it. This increases, so the density decreases. Right? So you can take this table and you can heat the table and it'll expand and its density decreases. Density is mass per unit volume. Water is a strange beast, and only in this temperature window. You see, you raise the temperature and instead of density going down, it's going up. Okay? And it's a very small effect, only 10 parts in 100,000. And you guys remember what was the effect of that? One of the effects of that? You try and freeze a lake. Remember that story?
Yeah, with the top part freezes.
That's right. Yeah. And that's important for life because then fish can swim and survive the winter. Okay. All right, so you saw that little bump in the curve was very important. Okay. All right, now here's another important concept, and that's very useful for us. Okay. All right, so most times if you add heat to a substance, its temperature will rise. Okay, so this is the heat added, its temperature will rise. There are times when you add heat and the temperature does not rise, it remains constant. Do you guys remember that? And that heat, this heat is called latent heat. Heat is Q. Okay. When does that happen? You're adding heat and the temperature is not changing. So, go ahead.
Oh, no.
All right. So here's one situation. So if you have ice at 0 degrees Celsius, okay, you add heat and the temperature will not rise. Okay. All of the heat is going into melting the ice. Okay. It's going into, all the energy is going into breaking the bonds, okay? Temperature will not rise till all of the ice is melted and it's become water. So when it's going from solid to liquid phase, when the phase is changing, then the temperature does not rise. All of the heat that you're supplying is going into breaking the bonds. Once it's done with that job, now it can raise the temperature, okay? So to melt 1 gram of ice, you need 80 calories of heat per gram, okay? And this is called the latent heat of fusion of water, okay? A similar phenomena happens when you boil water. You get water to 100 degrees Celsius, and now you add heat, and the temperature will not rise. It'll remain constant. So what's happening to all the heat? It's going into turning the water to steam. Okay, so it's making the water molecules go further apart, sort of breaking the bonds. Okay, and once all of the water turns into steam, now once it turns into steam, then you can raise the temperature of steam. Okay, you have to first convert all of the water into steam. If there is any water, all the energy you put in will go into evaporating the water. Okay, so this is called the latent heat of vaporization of water, and that's 540 calories per gram. Okay, so to convert, what this number tells you is, to convert 1 gram of water to steam, you need 540 calories of heat. And that's an enormous amount of heat. Okay, and so when 1 gram of steam at 100 degrees Celsius becomes 1 gram of water at 100 degrees Celsius, it gives off 540 calories of heat. Okay, to convert water to steam, you need to put in 540 calories of heat, and when steam condenses to water, it gives up 540 calories of heat. That's why steam burns are very dangerous. Okay, so this will burn you, and then this hot water will burn you as well. Okay, so when steam goes to water, it gives up a lot of heat. Okay, so that's why those two numbers are important to us, and that's called latent heat. It's called latent heat because it does not raise the temperature of the object. Okay? So again, latent heat of fusion for water is 80 calories per gram, and latent heat of vaporization for water is 540 calories per gram. All right, so we had covered all those concepts, and now we'll talk about evaporation. Okay? So let's go back to our app. Okay, so here's our gas at 300 degree Kelvin, 22 atmosphere pressure. And you saw that at any given temperature measures the average kinetic energy per molecule, but they're not going at the same speed. There are some fast molecules, slow molecules, and so on. The average speed is about 0.5 kilometer a second. Okay, so if you take a glass of water, so here's a glass of coffee, water essentially. Same thing is happening in this glass of water or coffee. The molecules are going at different speed. Okay, the molecules that are going at slow speed cannot escape, but the molecules that are going fast can escape the cup. Okay, so if I leave this cup here, all the coffee will evaporate. It'll take several days, but it'll evaporate. Okay, so, oops, what happened? All right, so you take a cup of water, the fast molecules will escape. Now, if in this room the humidity was 100%, then there are water molecules in the atmosphere, the number of molecules escaping will equal the number coming in from the atmosphere. Did you guys understand that? If the humidity is less than 100%, there's more escaping than coming in. Okay. So if in this room we maintain 100% humidity, this cup will never evaporate. Okay? All right, in this room, humidity is about 50%. Okay? Humidity of 50% is comfortable for us because if humidity of it's less than 50%, then our mucous membranes will dry out and stuff like that. That's not good. And our skin will dry out. Okay? If it's higher, if the humidity is 80%, then what's the problem? You should know the answer to this now. Huh?
Can't sweat.
No, you can't sweat. Your sweat will not evaporate. Okay? And every time 1 gram of your sweat evaporates, it takes over 540 calories of heat. That's the best mechanism for getting rid of heat. Okay? That's how you maintain your body temperature. Okay? So that's very important to us, the right level of humidity. Okay? So what makes evaporation in, okay, water and other substances can evaporate at temperatures far below their boiling point. A glass of water will slowly evaporate away in a few days. Okay. Ice can sublimate directly to water vapor. Okay. A solid doesn't have to go through liquid and then to the gas phase. Ice can directly evaporate, but there has to be very little moisture in the atmosphere for ice to directly evaporate. Okay, so for instance, this graph tells you that. So here's a phase diagram of water. You have phase diagrams for all substances. What this tells you is, see, this is pressure versus temperature. What this tells you is, at this pressure and temperature, this substance can only be in solid state. Okay, so it tells you under these conditions what state it can be in. For this pressure and temperature, H2O can only be in the liquid phase. Okay. What these lines tell you is for these pressure and temperature, it can be both in solid and liquid phase. Okay, so at temperature of 0 degrees and okay, so this is roughly 1 atmosphere and 0 degrees. Okay, so when you see a glass of ice water, you know it's at 0 degrees Celsius. Okay, it doesn't matter where it is at. Okay, so if you see a mixture of ice and okay, it's at 0 degrees Celsius. All right, all right. So humid. Okay, so now we'll define relative humidity. Humidity is so why is relative humidity important? If it's 100% humid, then you can sweat all you want, and your sweat won't evaporate, and you won't be able to cool down. Okay, so that's why humidity is a important factor for us. And let's define relative humidity. So what this table tells you is the following: saturation density of water vapor in air. What do you think that means?
Water vapor in there.
I'm sorry?
How much water's in there? Yeah, water vapor in there.
Yeah, okay, so what this tells you, the saturation tells you is the maximum water vapor the atmosphere can hold at these temperatures. Okay, so it tells you the maximum water vapor it can hold. Okay, so in this room, the temperature is 20 degrees Celsius right now. So at 20 degrees Celsius, it can hold a maximum of 17.3 grams per meter cube. Okay, here's a meter cube, this thing. 17.3 grams is about a half a mouthful of water. Okay, so that's the maximum it can hold. So if there's that much water vapor, then that's 100% humidity. Okay, so if it can hold the maximum. If there's 8.65 grams, which is half of that, that's 50% humidity. Okay, and if there is 1.73 grams per meter cube at this temperature, what is the humidity? 10%. Okay? If the humidity is 10%, All you have to do is you even think about sweating, and that sweat will evaporate. Okay? What will happen? Your skin will dry off, your mucus, your nose, nostrils will dry off, and you won't like it. Okay? All right. So people find that they're most comfortable when air has a relative humidity of 40 to 50%. Okay? Lower humidity dries out our skin and mucous membranes and can cause sinus trouble and other respiratory problems. Higher humidity suppresses the net evaporation rate of perspiration and may cause you to feel uncomfortably warm even at moderate temperatures. Okay? So, by the way, we spend a lot of money to make you guys comfortable. You know, the college spends roughly about $6 million in electricity bills. And a lot of money goes into maintaining this comfortable humidity, 40 to 50%. All right, so you know we are warm-blooded animals. We maintain a temperature of 37 degrees Celsius. Okay. Now, cell metabolism increases with increasing temperature. What does that mean? So more reactions are going on. Reactions are going on faster in your body when your body temperature increases. Okay, and when your body temperature increases, then your reactions are going faster and you're producing more heat. You're already warmer and you're producing more heat. And then you'll get warmer still. So that's a vicious cycle, okay? So increased metabolism generates more than normal amounts of body heat. And this can cause temperature to increase further if you're not able to get rid of the heat. Okay? A vicious cycle results if the body temperature rises about 42 degrees Celsius. The body's cooling mechanism cannot keep up with it. Okay, so you cannot get rid of the heat fast enough. Look at this. 37 to 42 degrees Celsius. Okay, that's 5 degrees Celsius increase, which is about 10 degrees Fahrenheit. Okay, 108 degrees Fahrenheit, your body can't cool yourself. So you have a 15% room for error. What's that? No, well, no, so it can't cool down itself after 108 degrees. Your body naturally raises its temperature. Let's say when you have a fever, you raised your temperature to kill the infection, to help kill the infection and all that. Okay, but if it goes out of hand, then you're in danger. Okay. Similarly, and problem exists when body temperatures become too low, cell metabolism decreases. So when your body temperature lowers, your metabolism decreases, you're producing less heat, and then your temperature will fall further. Okay, so you don't want your body temperature to rise too much or fall too much. Both are dangerous. Okay. Okay. So a 130-pound person, the basal metabolic rate, that means the normal functioning reaction rates are producing 80 joules of heat per second. Okay, so a good one to remember is roughly a 150-pound person is glowing like a 100-watt bulb. That's how much heat you're producing per second. Okay, so if you want to maintain your body temperature, what does that mean? You have to get rid of 100 joules of heat per second. Okay? And look at this amazing thing. Okay, and then you go for a run. Now, from a 100-watt bulb, you become a 1,500-watt bulb. I'm talking about a 150-pound person. Okay, so you go for a run, you're producing 1,500 joules per second. You don't want your body temperature to rise, so your air conditioning, your cooling system has to work 15 times harder. Okay? And your body is amazing. It just turns it on just like that. Okay? So how do you remove this excess heat? It takes, you saw that 540 calories of heat to vaporize 1 gram of water. So what you do is, again, like we said, you sweat. Okay, that's, you've done half your job, and now you hope like hell that the sweat evaporates, because that's when the heat is taken away. Okay? So for instance, if you put a treadmill in a sauna, that won't work, right? Your sweat won't evaporate. Okay. All right, look at this diagram. What is this showing you? So this is showing you the outside temperature is 45 degrees Celsius. Your body temperature is 37 degrees Celsius. Okay. Heat is you're producing 100 watts of heat, 100 joules of heat per second. That's your normal basal metabolic rate. The outside temperature is hot, and you're getting heat from the outside. You're getting 100 watts from radiation. Okay, everything emits radiation. So right now my temperature is greater than the temperature of the wall, so I'm losing energy via radiation. But if the temperature outside is hotter than my body, then I'm gaining heat via radiation. You're gaining almost 100 watts. Okay? So the only way to get rid of heat is when you sweat and the sweat evaporates. So if the outside temperature was that and the humidity was 100%, then it's goodbye, baby. Okay? So high temperature and high humidity would be very bad. Okay? The only way to lose heat would, okay? Evaporation of sweat is the only method of cooling off that works when surrounding temperature warmer than body temperature. Okay? And also, by the way, when we breathe out, okay. So when when somebody overheats, it's high temperature and high humidity. How do you cool them down the fastest? What's that? Alcohol rub. What you want to find is something that evaporates and something that's zero humidity. And alcohol, there's no alcohol in the atmosphere, so you give them an alcohol rub, and that every time alcohol evaporates, it will remove heat from your body. Okay? And so this problem goes through that. The thing is, okay, the heat of vaporization for alcohol is 240 calories per gram. What does that mean? 204 calories per gram. Every time 1 gram of alcohol evaporates, it takes away 204 calories of heat. Okay. What was the number for water? 540. Okay, so now you know why we don't sweat alcohol, we sweat water. This is much more efficient. Okay. All right. You saw that heat is transferred from a hotter object to a colder object. Okay? And there are 3 mechanisms for transferring heat. Okay? Conduction, convection, and radiation. Okay? So this diagram illustrates all 3 methods. Here's a metal, and so heat is conducted via the metal to your hand. You can get heat that way. You can hold your hands there, and your hands will feel warm, and you're getting energy via electromagnetic radiation. How are you getting heat here? I'm sorry?
You're holding your hand over the heat.
Right. Wow. So how is the heat reaching you?
Transfers to your hand.
Yeah. Well, radiation, some of it, but there's another mechanism by which you're getting more heat. How are you getting heat here?
Conduction.
No, it's convection. Okay, so here's what's happening. Okay, the air around this fire warms up. When air warms, what happens? It expands. it gets lighter than the surrounding cold air, and that'll rise up. So warm air is rising up, and the heat is reaching to you via the motion of warm fluid, and that's convective heat transfer. Okay, so warm fluid is rising up and bringing the heat to you. Okay, and this is important in our body. In our body, our blood is warm. Okay, and when you're overheating, what happens? Your heart pumps warm blood to your skin, where you can sweat and the sweat to evaporate. Now that's forced convection. This is natural convection. Okay, so in your body you have a mechanism for controlling heat loss or heat, and you can control heat loss. If you want to lose heat, then you pump blood to your skin. And if it's cold and you don't want to lose heat, you constrict the blood vessels there. You don't let blood go to your extremities. Okay, so that's forced convection. But this is a natural convection. Okay, so this air warms up, it rises, and that's what's the warm air is transferring heat to you. All right, so conduction. Okay, so here's a solid, and conduction is important in solids. So this end of the solid is hotter, meaning these atoms have greater kinetic energy than these guys. And so what they do is they bump into their neighbors, transfer some of their energy. These guys bump into their neighbors, transfer some of their energy, and so on. How long does this go on? How long will this go on?
Keeps going on until it's cool.
I'm sorry?
Will it just keep going until there's no more?
No. Okay, I make this table hotter. You know the answer. This end is 100 degrees Celsius, that end is 0 degrees Celsius. And I'll let go of this. Heat will flow from here to there till when?
It'll reach the same temperature.
Exactly. So till the average kinetic energy of all the molecules are the same. Okay. So this is the best example of socialism. So till the temperature has become equal. So now let me think before you answer. Now has all heat flow stopped?
No, it
So what's
moves
happening?
It just changes, the energy was somewhere else.
No, you answered the first part right. So there's no net heat flow. These guys, if this guy gives them $1, he gives them $1 back. So there's no net heat flow. Heat flow hasn't stopped, okay, but there's no net heat flow, okay? All right, again, why are we concerned about this? See, if it's cold outside, heat is flowing out of the wall. I mean, that's real money going out of the wall, okay? You want to cut that, okay? And so you want better insulation, and that's what this number is. The higher the conductivity, this is thermal, okay? So this is the rate of heat flow, how much heat is flowing per unit time. K is the thermal conductivity of the material. A is the area of the wall, okay? And, so that's why we don't have windows here. I mean, windows are pretty, but they cost a lot of heat flows out the window, okay? So, higher the temperature difference, this is hot inside and cold outside, and that's the thickness of the walls, okay? Thicker the walls, less the amount of heat flows, okay? So this is thermal conductivity. Heat is, so that's what that tells you, okay? Convective heat transfer, so you have a space heater, it warms up the air expands, gets lighter, it rises up, okay? And so there's a low pressure here, and cold air comes in, replaces that, and eventually all the air gets warmed up. Okay, that's a bad way to heat the place. You put a heater here, you gotta heat the whole room air to warm up. Right? All right, you guys have all heard of wind chill. What does wind chill mean? Do you? What's that?
I said chilling wind.
Yeah, chilling wind. Okay.
Just like I said, so
So here's the deal. air is a bad conductor. Okay? So it can be as cold as it wants. If the air is still, you'll be fine. You know, you can feel the smallest crack in your house if there's the slightest breeze. And the reason is, okay, if the air were still, you could warm a layer of air around your body, and if somebody promises that it won't blow away, then you'll be fine. It's this layer of air that you warmed up next to your body, if that gets blown away, that gets replaced by cold air, then you lose heat. Okay? So if you keep blowing this warm air away, then you're losing heat faster, and that's what wind chill becomes. So this table tells you that, and now there's, you can't, it's very hard to come up with a formula for that, and so they just have these tables on how it feels. Okay, so this is, what this is this is the temperature of the air that is still. Okay, so let's make sure we understand this table. So if you have an air that's at minus 10 degrees Celsius, now if this air were blowing at 2 meters per second, this air would feel the same as minus 12 degrees Celsius air that was still. Okay? If it were blowing at 10 meters per second, the minus 10 degrees Celsius would feel as minus 29 degrees Celsius. Okay? So what that is saying is 10 degrees, minus 10 degree air blowing at 10 meters per second would feel the same as minus 29 degrees air that was still. That's what that means. Okay? All right, so again, when the wind blows, you lose heat much faster. And that's your main concern. Why is that your main concern? Because you're warm-blooded and you want to maintain a constant body temperature, okay? So you want to maintain a constant bank balance, and if my son is spending too much money, that's a thing of worry, you know? Yeah, so that's the stuff. Okay, so you saw that all objects emit electromagnetic radiation. So here's a infrared picture. Remember in convective heat loss, where is most of the warm air is there, okay? And that emits infrared radiation. See, there is the infrared picture. That's where all the warm air is, you know? So if you're cold, you should really go spend time in the attic. Okay? All right, so every object emits electromagnetic radiation, and this is the rate at which you're losing heat from electromagnetic radiation. This is called this is a constant associated with the property of the surface. Emissivity, it's a number between 0 and 1. This is a constant that's the same for all substances. It's called the Stefan-Boltzmann's constant. Okay, Stefan's constant. That's the area of this object, and that's the temperature to the power 4. Okay, so you raise the temperature of some object, you lose a lot more heat. Double the temperature, and you lose heat 16 times as high. 2 to the power of 4 is 16. Okay? Now, so for newborn babies, what's the difference between a newborn baby and us?
They don't have like a way of regulating their temperature, or maybe they're not as
Yeah.
experienced.
Yeah, well, and so it takes a few hours for the bodies to, but here's the problem with little babies. Their surface area, so per pound, they have a lot more surface area, okay? So their surface area to volume is larger. Larger the surface area, greater the heat you lose via radiation, okay? So, so you gotta make sure you cover them well and all that kind of stuff, okay? All right. Now, this is the heat lost by an object, but if you're surrounded by other objects, then you're getting heat from them, okay? So this is your temperature and this is the surrounding temperature. If your temperature and the surrounding temperature is equal, then there's no net loss of heat. If the surrounding temperature is lower, then there is a net loss of heat. And if the surrounding temperature is higher, then you're gaining heat, which you saw, which is enormous. See, I mean, that's a warm temperature. 45 degrees Celsius is about 120 degree Fahrenheit. We don't see that in Florida, but I mean, we come close some days. You're getting as much heat via radiation as you're producing by your basal metabolic rate. Okay, so that can be substantial. All right, so, okay, so this tells you, and what this image shows you is, see, it illustrates the fact that at our body temperatures, we're mostly emitting infrared radiation. So here is, we're not emitting any visible light, okay? So in a camera taking a picture using visible light, you can't see the person's arm, but a camera taking a picture using infrared light, you can see the person's arm. Okay. See, the emissivity E is a number that's between 0 and 1, okay? 1. And if it's closer to 1, that means it'll absorb all the radiation falling on it, okay? Closer to 1, it absorbs radiation, and you know, it's also a good emitter. So in the winter, what color clothes do you like to wear? You like to wear dark clothes. So dark clothes have E equal to 1. All the radiation falling on it is absorbed, and you get warmth from that. Okay. In the summer, what do you like to wear? Light colored clothes, because E is less, and radiation falling on you is reflective. Okay. So clothing, dark fabrics are good absorbers, while light colored fabrics are better reflectors. So okay. Dark fabrics have E equal to 1. Close to 1, and light colored fabrics are close to 0. Okay. When surrounding temperatures are low, if it's cold outside, you're losing heat to the outside. And to maintain body temperature, you would have to produce more heat. Okay. Okay. And it's necessary to limit rate of heat loss of the body. So what are the mechanisms the body does? The body does not sweat as much in cold weather, because every time sweat evaporates, it takes away too much heat. There's still evaporation of water from the lungs. Every time you breathe out, there's some moisture in there, so you can't avoid that. Okay? Thick layers of clothing reduce the rate of heat transfer by conduction. Okay. Okay, so you saw, what was the wind chill factor? Every time wind blows away that layer of warm air, that gets replaced by cold air and stuff like that. Okay? And so you lose heat a lot that way. So how do animals that have to be outside handle against that?
Their fur and hibernating, like their coat.
Yeah, well, but if they have to be outside,
Then their coat.
yeah, their coats. So they have a thin their layer of very fine coat, which has small fibers which trap air, which does not let that air be blown. Okay, so that's how they. Okay. So conduction, convection, and radiation. With insufficient clothing, the body loses more heat than it produces. Its temperature drops, and uncontrollable shivering sets in. Why do we shiver?
Because we're not maintaining homeostasis.
So why do you shiver?
To create body heat.
Very good. So here is an amazing number. Okay, so shivering is a clever use of opposing muscles to do work against one another. Most skeletal muscles are involved in severe shivering, resulting in little work and a lot of thermal energy generated. Look at this. Energy consumption during shivering is about 425 watts, about the same as cycling. So shivering is the same as cycling. Yeah. All right, so if you can learn to shiver sitting down in the summer, then you don't have to go to the gym. So conscious physical activities are also used, such as rubbing hands together. So you're generating heat that way. Okay, okay, what is frostbite?
Not when you get too cold, like you're extremely
Okay, yeah, so okay, here's 1 gram of water. And if I freeze it, what will happen? I'm sorry? It becomes ice, and its volume increases by 10%. Okay, so volume will increase by 10%. Now let's do this inside a cell. So inside a cell, you have mostly water, and you freeze this water, its volume would increase by 10%, and the cell would burst. Okay, so that's what happens in frostbite. The water inside a cell freezes, expands, and kills the cell. Okay, damage done to foods when frozen are due primarily to cells bursting by the expansion of water turned to ice. This is why frostbite is dangerous. Okay, some foods tolerate being frozen better than others, but none tolerate repeated freezing and thawing. Okay, so here's a normal healthy skin, early stages frost nip, superficial frostbite, and deep frostbite. So all those cells have died. Okay. Therapeutic heat, the mechanism of relief by elevated temperatures seem to be twofold. Relaxation of muscles, when you have sore muscles, heat can be used as a therapy, and increased blood flow. So if you warm a body area, your muscles will relax, and there's increased blood flow. And with increased blood flow, you do whatever repair that you have to do. Okay, so newborn infants are sometimes placed under infrared heaters. Infrared rays penetrate deeper into your body. Heaters. To replace the heat they would have received from their mothers. Within a few hours of birth, an infant's temperature control mechanism works well enough. Okay, so it takes a few hours for the infant's temperature control to work. Okay. The removal so sometimes you use ice packs as well as therapy. I guess the removal of heat from the body can also be therapeutic. Okay. Lower temperature acts as a local anesthetic. Okay. So I guess it dulls pain and stuff like that, and so that's why you do that. Children who are teething are fond of sucking on ice cubes to relieve pain. Okay. All right, guys, so that finishes this chapter.